the molecule. Okay? So we don't really have a predefined angle of rotation. When we're actually rotating along the axis, nothing is changing. Okay? So the C infinity axis is only when we have this linear type of molecule where we can rotate about any angle we like. Okay? So when we have that as our principal axis, then we can also have a vertical plane. And that vertical plane, we can perform the reflection, an infinite number of vertical planes that you can perform reflection about, and it doesn't change the molecule. Okay? So these are going to be, pardon me, these are going to be heteronuclear diatomic molecules or polyatomic molecules. Hetero, they have to be different. Okay? We don't have something that is in the center serving as an inversion center. The variation on that is a linear molecule where there is an inversion center. So in this, what we get is something called D infinity H. Okay? Because, again, we have this rotation. It can be through any angle. We'll look later at the differences between C's and D's, but the D is, again, a type of rotation. Now we have a horizontal plane that is permitted. We can cut this down here with a horizontal plane. Remember, this is vertical because that's our principal axis. So if we put a vertical plane here, it reflects one side onto the other. Same here with your carbon dioxide. The center here, we could treat that as a horizontal plane that reflects one side onto the other. So homonuclear diatomic molecules like hydrogen, oxygen, and so on are going to be this group. Linear polyatomics, where we have this inversion center, are also going to fall into that group. In the inorganic compounds, square planar is a fairly common orientation. This is D4H. D4 because we have a 90-degree rotation. So our principal axis would be vertical this way. All the arrows would be on a horizontal plane. So this is where the H is coming from. Tetrahedral geometry is denoted TD. Okay, so something like the methane molecule or the phosphorus, the B4. These are both in a tetrahedral geometry, octahedral geometry, OH. So these are some of the more common ones, what we're called special point groups. Ones that you may be able to identify immediately by just looking at the molecule and say, yeah, that's one of those, and you can identify it quickly. I know I've gone through that fairly fast. Any questions about any of those so far? Okay. So the reason I've gone through some of these common ones is so that you can do them quickly. You can't identify them simply by looking at them. Then you need to go through a process. The ones that I've discussed so far, they either have very high symmetry or they have very low symmetry. So it's usually easy to pick out what the point group is. The molecules that are somewhere in between are the ones where you need some sort of systematic method to determine what the point group is. And when you're trying to establish what these point groups are, you need what's sometimes referred to as a decision tree or flow chart, a method of going through the symmetry of a molecule, looking at certain aspects of it, and it's like, do you have this, yes or no? If it's yes, you branch one way, if it's no, you branch another. You keep on going through that decision tree to ultimately establish what the point group is. This is the decision tree that's in the course kit. I know it looks awful. There are variations on it. I'll be showing one that's on a website that it looks different, but it really comes down to the same thing. And pardon me, believe it or not, you'll get accustomed to working through this. And you'll be able to establish what the point groups are. That they have some regular steps to it, and after you work through them, you'll be able to establish the point groups fairly readily. So what I'm going to do is link to the website. These links are on the Google site as well, where the notes are. And as it says, this is the website. It has a somewhat different decision tree than the ones in the course kit. And there's also what they call the Symmetry Challenge page at that site. Different examples that you can work through to check out the decision tree. So I'm just going to let you do it. Okay, so this is the decision tree that is for that particular website. So it looks a little different. The way it goes through it isn't quite the same as the ones in the course kit, but it comes to the same conclusion. So you can see that what it does, you come down, you start with your structure. Is the molecule linear? Yes, you go this way. No, you go that way. And each one of these you move through and make the appropriate deviation depending upon your yes or no response. So I'm just going to go to this page here. So what's appearing here is that decision tree or flow chart. This is just focusing in on one part of it so that we can work through it. So, okay, let's work with the boron. It's the same sort of idea as boron trichloride. So we start out first, is this a linear molecule? Yes or no? Well, I'm going to say yes, and I get a little ring. You say yes, the flow chart shakes around and goes, no. That's not correct. Okay? So it isn't linear. So we say, okay, no, it's not linear. So then the next question is, does it contain two or more unique C3 axes? Well, it's got one. I'm going to say, well, yeah, it does. Oh, no, two or more. Well, no, it doesn't have two or more. So I'm going to come down here. Does the molecule contain a proper rotation axis? Yes, it has that C3. And it'll even draw it in there for you to show where it is, and what we have is a C3. Okay. What's the highest order rotation axis? So the C3 is our highest order. Are there n perpendicular C2 axes? Well, we know that we can do a C2 about each one of these borons and hydrogen bonds. So, yes, there's a number of, and it shows where they are. And there's our C2 axis perpendicular to the principal C3 axis. Does it contain a horizontal plane? Well, remember that our principal axis is defined vertical. So the molecule is actually resting like that. And this is horizontal. So it does contain a horizontal plane. Okay, there's the horizontal plane. So this is now the point group. We have to remember that the principal axis, it was the C3. So this N is 3. So the point group for the boron or the boron trichloride would be D3H. Okay. So I recommend you go through a number of these, practice them. We've got all these different ones. Like there's a lot there to practice. Okay. And we just pull up water. Okay. Water molecule. Is it linear? No. Does it have two or more unique C3 axes? No. Does it contain a proper rotation axis?